you'll notice here that for Judson, a binary operation automatically takes values in the set. So binary operation on a set G automatically takes its values in G. Other authors don't assume that. Okay? So other authors, other sources, or other authors will say one of the axioms, one of the group axioms, it's generally the first one quoted, is closure. And this is the statement that says for every G1, G2, and G, the result of the operation G1 with G2, G1 circle G2, whatever that operation is, they will say that that has to, one of the axioms is that this is an element of G. Okay? And they separate it off and it's called a closure axiom. And then they have the other three axioms: existence of identity, associativity, and existence of inverse. Judson presents it in a way that a binary operation for him is automatically closed of the set. So it's an operation that takes pairs of elements from G and gives you values in G. Okay. Other authors don't. Other authors have a weaker notion of a binary operation. Okay. Both definitions are equivalent. Okay, so the idea of closure for group operation is important, and it will be one of the matters that we'll have to be checking for things like subgroups. And it is an important notion because, for instance, you can have reasonable operations that wouldn't be closed on the set. For instance, you can have the integers and think of the operation of division. Take any two integers, you can divide one by the other. 15 divided by 5 is 3. But sometimes 3 divided by 15 gives you 3/15, which is not an integer. So division will take you out of the system of integers. So the integers is not closed under division. Okay. So it is an important notion. But it's just in his definition of the group, it's maybe slightly pushed up into the introductory paragraph, and you might notice it, or you might notice that it is in fact the same as other definitions. Okay, then we worked our way through the various examples that he lists in examples 3.8 through 3.15. And then we come on to this next section, which is basic properties of groups. Okay, so these are some of the immediate consequences of the group axioms. Okay. And what I'm just reading from the book, we'll just lay out some of these. So these are little proofs, 2 or 3 line proofs that are consequences of the group axioms. Okay, they're true for every group, and just give us some, common properties that we're going to be using all the time. And the first is to say that the identity element in a group is unique. See, the axiom doesn't explicitly say there is one and only one element, which is the identity. It says, the axiom says there is an identity, which maybe leaves it open that there could be more than one floating around. Okay? And you might imagine some kind of a weird mathematical object that does have a few identities. Things that when you operate on other elements leave them unchanged. But when you think about it a little bit, you see that that can't happen. Okay? So this says the identity element is unique. So suppose E1 and E2 are both identities in G, in a group G. And my presentation might be slightly different to what he has in the book. But what we do then, and we'll assume that the group, that the operation is circle. Pretty soon we'll drop the symbol for the circle and we'll just write products. It's just simply products of the variable names. We won't bother indicating a symbol for the operation when we're talking about these things in general. Okay. Is unique. Identity is unique. Sorry. So, well, the proof of this is quite direct. We simply consider the element E1 circle E2. You're writing this down, put that in the middle of the line, middle of the page. Consider E1 circle E2. Now, E1 is an identity element. So by definition, E1 circle E2 is equal to E2. Yeah. Justification for this equal sign is since E1 is an identity. But equally well, E2 is also an identity, because we supposed it was. And when you operate with E2 on any other element, it leaves the other element unchanged. So this is also equal to E1. Justification for that is since E2 is an identity. So this element, which does exist in the group, because you've got the binary operation on the group, so there will be some element in the group which is E1 circle E2, but it is simultaneously E2 and E1. You can't have a thing being simultaneously two different things. So E1 must be the same as E2. So it's impossible to have two distinct identities. This shows that they must be the same. So there is only one identity in a group. Okay? It's just an immediate consequence of the identity property. It can be one and only one. Identities. Now you could have said, well, why didn't the group axiom just say a group has one and only one identity? Why did they build it into the axiom? Well, generally with axioms, you want to make them as kind of weak as possible. You don't want to build in superfluous information to axioms. You just want to make them as minimal as possible. So since the fact that they're unique is a consequence of the notion of an identity, the definition, you leave it out of the axiom. 3.18, similarly, inverses are unique. So again, this isn't stated explicitly in the axiom. The axiom says for every element in the group, there is a other element which plays the role of the inverse to that first element, but it doesn't say there is one and only one. So when we first meet it, it is plausible, perhaps, that for an element G, there could be two other elements, that when you operate on them with G, you get the identity element. And it's initially plausible that those two other elements, two other inverses for G, might be different elements. But again, by considering a carefully chosen product, we can prove that that's not the case. Okay. So suppose an element G, little g, G has two inverses. G, and the notation uses in the book, I'll use it here, G prime and G double prime. I'm not saying explicitly that they're different. But just suppose there were two elements around in the group that are inverses to G. So the property that each of these has is that when you operate on it with G, circle operation on either side, it gives you the identity element. We know identity elements are unique. Okay. So for this one, we again consider an appropriate product, and the appropriate product is G circle G circle G prime prime. So G prime circle G. So we multiply G on the left by one of its inverses, and on the right by the other of its inverses. Now by associativity, I don't have to take the bother to bracket this up. But I will do. I mean, this triple product, we could either consider it like this or bracket it up like this. Okay. Associativity tells me that these two are equal. Justification for that is associativity. But when you do this one, you see G prime multiplied by G. Well, G prime is an inverse for G, so this is going to be the identity with G double prime, so that's just going to be G double prime. Okay, this equation is true because G prime is an inverse element of G. But when you go the other way, G with G double prime is an inverse, so it's the identity, so it's G prime. Okay.
So again, from beginning to end, you've got G double prime is equal to G. So what maybe might have been two distinct inverses for the element G in the group turns out with a combination of associativity and the existence of, and the property of being an inverse, that's really all it is. Combining associativity with the property of being an inverse means, in fact, G prime has to be the same as G double. Okay. So when we speak of inverses, they are unique. For any particular element, there is one and only one inverse. It may happen to be the element itself. An element can be its own inverse. But there's one and only one inverse for each element. Okay. Any comments on that? So I won't step through each and every one of them, but let's just look at the statements of the other remaining elements. So you see here, we're just using the basic group axioms, nothing else, to draw out some further properties that every group has. We're not saying which group we're talking about here, it's just a group. So we're simultaneously talking about every group. The other properties that there are of similar ilk. Property 3.19 says, now this is extremely important and extremely universal. If you take the inverse of a product, it is the product of the inverses within the opposite order. Okay, that should be pretty much hardwired into you by now. Have to do matrix multiplication and stuff like that. Okay. The most interesting groups are groups where, like the symmetry group of the triangle or the rectangle we showed you, a lot of the most interesting groups are groups where actually the elements are interpreted as functions or transformations, and the group operation is composition of operations. Okay? And then you really appreciate how this is like a universal law of reality. Beyond physics, it's just true that the inverse of a composition of operations is the composition of the inverses within the opposite. Okay? You do this every day when you dress your feet. How do you dress your foot in the morning? Sock shoe. Sock shoe. How do you undress your foot? Shoe sock. Shoe sock. You take off the shoe first and then the sock. Okay, so that's exactly what you're doing. This is what you do in the evening. You invert the operation of dressing your foot, but this was how you dress your foot in the morning. First, you put on your sock, B, then you put on your shoe, and you undo those operations by first taking off your shoe and then taking off your sock. These are interpreting these things as compositions of functions. Okay. Same as getting yourself dressed and putting on underwear and then outerwear, but I thought it was a bit risque, so I reduced it to shoe where I'm completely safe ground. No reference to underwear. There we go. Proposition 3.20. This is interesting. The inverse of the inverse is the original element. Yeah? You're familiar with that in the context of matrices, or inverses being interpreted as the reciprocal of a number in those other contexts. Well, it's true in general for groups. Okay? So a lot of these things that we know in specific groups, they're just examples of general groups like this. Cancellation in equations we can do. So if you got an equation like this, ax equals b, you think of it that you know what a and b are. X is some unknown quantity. Well, this has a unique solution. What's the solution x to this equation?
B divided A.
Well, avoid saying divide.
Oh.
Yeah. So A inverse on the left and B on the right.
Yeah.
Because you have to multiply both sides on the left by A inverse, and then they cancel to leave you with the x.
B.
So this one, what's the solution to x to that one? B A inverse. Yes, to cancel the A, we must multiply on the right by A inverse. Yes. That's all the proof is saying. Okay, so those equations have unique solutions. So we can cancel in these simple equations like that. And one particular example of that is when you see the same element on both sides in a product, you can just forget it. and the remaining factors must be equal. Okay. So if you see A on the right of a bunch of other stuff, or indeed equivalently A on the left of a bunch of other stuff, you can just be cancelled out and the remaining factors must be equal.
And when you look at the proofs of those, they're all along the lines of the few I sketched out there. And you'll notice in all these proofs as well, so when he presented these arguments here, you see he wasn't putting in the circle for the group operation. So we'll now allow ourselves to do that. So although strictly speaking, it's good to remember that a group consists of a set with a certain operation on it. And it makes sense in the early days to have a symbol for that operation, even when you're talking about it in general, so you can clearly see the operation at work. But we quickly now, or we need this, because otherwise you can save yourself the work of writing all those circles. Because really, those little circles always go in between pairs of elements. So it's understood that they're. So we can look at products like this. And remember, these aren't necessarily multiplications of numbers. I mean, they might be. If the group is a group of number-like things, the operation is multiplication. But more generally, this is just a product of elements from some group. Okay? So you can imagine, if you like, little circles between each of these representing the operation, but we dispense with it now. So this is known as writing the operation multiplicatively. We write it as if it were multiplication. Okay? And an extension of that idea is we allow ourselves to talk about powers. Because, what would we mean by g to the power n inside a group? We would mean g, product of g with g, g with g with g, n times. Where the product that's going on here is the group operation, whatever that is. Similarly, we allow ourselves to talk about a negative power of the group element. You assume n is positive. Now you can't, the first definition doesn't work, so you can't have a negative amount of copies of the thing. Yeah, you just can't. It doesn't make sense. But what we mean by a negative power of a group element, we mean the corresponding positive power of the inverse element. Yeah, so group, every element in the group has an inverse. So g to the power minus n, we find the inverse element level g, and we take the positive nth power of that inverse element. That's the meaning of this notation. That's the meaning we attach to this notation. So this isn't some kind of weird result you have to understand. This is just a definition of this piece of notation. What it means to say g to the power minus 5. We just mean by that g inverse multiplied by itself 5 times. It's not a deep result that some weird way g to the power minus 5 is g inverse to the power 5. It's just a simple matter of defining what we mean by this notation. Similarly, g to the power 0 will represent the identity element. Again, it's not a deep, weird result. It's just a matter of defining what is meant by g with a superscript of 0. Yeah. But then the normal rules for manipulating indices apply. Ones you're familiar with, if these were numbers and powers in the sense of multiplication of numbers, but the same rules apply. So a product of powers is a power where the exponent is the sum of the exponents. You've just got a bunch of g's here multiplied by a bunch of g's there. In total, you've just got n plus n g's multiplied together. Similarly, a power of a power is a power where the exponent is the product of the powers. Okay, and with inverses as well. That's just showing, if you substitute the inverse elements and make the power negative, it's still the same. Okay. So we're going to go on to subgroups now, but any questions that arise out of looking at the axioms and some of these initial consequences? Okay. Okay. So subgroups. Okay, you're already quite familiar
with this, all your work with vector spaces last year, you had the notion of subspaces. So vector space is some kind of algebraic structure. It's a set with two operations on it, an addition and a scalar multiplication. It's a large set, with lots of elements in it, and these operations. A subspace, a vector subspace, is some subset of that large set, which acts itself under the same operations, the same addition, the same scalar multiplication. It acts like a little vector space all by itself. Okay? The definition for a subgroup is precisely the same. Okay? Group is some set with a meaningful operation on it, just one operation. Lots of elements in it, operation going on. But a subgroup is just some subset of that, which under the same operation forms a group with respect to that operation. Now some examples here he picks out. So one familiar group we can talk about is R star. R star is the group of non-zero real numbers under multiplication. So just the familiar real numbers under the operation of multiplication, except you have to get rid of zero because zero doesn't have an inverse. You don't lose anything by getting rid of zero because zero times anything is equal to zero. So it's not that interesting an element of multiplication. So that's a perfectly good group. It has an identity element, 1. It's closed under the operation. You multiply two real numbers, you get another non-zero real number. It's got inverses. Inverses are the reciprocals. The inverse of x is 1 over x. Inside non-zero real numbers. So an interesting subgroup of that is the subgroup formed by all the non-zero rational numbers. Okay? So rational number, remember, is a ratio of integers, p and q. But we exclude 0. So we can assume now that both the numerator and the denominator are non-zero. Okay? So any fraction of integers like that is a non-zero rational number. And that's a subgroup under that very same operation of multiplication. So you take any two rationals and multiply them. How do you multiply p over q and r over s? It's simply pr over qs. So this again is a ratio of integers, non-zero integers. P, q, r, and s will. So the thing is closed under the operation. It has an identity because the identity element is 1. Remember, identities are unique. So the identity that the subgroup has to be the same as the identity that the enclosing group has. 1 is certainly in this picture because 1 is equal to 1 over 1. 1 is a rational number. And it also has all the inverses because the inverse of a rational number p over q is simply q over p. That's the way multiplication of fractions works. Inverse of p over q is q over p. And that again is certainly a ratio of non-zero integers. So the set of non-zero rationals is certainly a subset of the non-zero reals, and it acts like a little group itself. Little, it's still big. It's but it is strictly small because it's countable. Remember, you can list all of the rational numbers, but you can't list all the real numbers. I'll show you that sometime too. So it acts like a group all the time. The non-zero complex numbers are another multiplicative group. You can identify, for instance, this subgroup. Okay, this is a very small subgroup of it. It's just only got 4 elements in it. 1 minus 1, I minus I. That forms all by itself a closed system under multiplication. You take a product of any of these two, or square any one of them, you're again within the same set. So it's a closed system. It's got the identity element, 1, the complex number 1. And it's got all the inverses. Okay, the inverse of I is minus I. The inverse of minus 1 is itself. The inverse of 1 is 1. The inverse of minus I is I. So it has all the necessary inverses. It's closed under the operation. It has the identity. So it's a subgroup. There's other examples there that you should read through. Any questions about just the notion of a subgroup, definition? So it's familiar to you from practice subspaces. I think I made that point in the group reading notes.
But we look at these subgroup theorems. So the issue will be, in many situations, we'll be concerned with identifying the subgroups of the group. The subgroups that a group has, in some way, are a measure of its structure. A group that has lots of complicated subgroups is a very rich structure. You've got some algebraic system, a group, and within it, there are loads of little groups. You would call that it has a rich structure. There's a lot going on. Similarly, some groups have a very small amount of subgroups. They may have a very restricted amount of subgroups. Sometimes they have none at all, apart from some trivial ones that are always present. In that case, you'd say the group is kind of simplish if it doesn't have a rich subgroup structure. So the amount of, it's worth writing down, the amount of subgroups, the amount and nature of a group's subgroups the amount and nature of a group's subgroups is a measure of the complexity, or I'm not using these in any technical sense, the complexity or the richness of the original group. Okay. So a common problem or a common task we'll have to do will be identifying, and he probably makes the same points in this discussion, but these are the important things, will be identifying when a given subset, so I might lay a group out for you, right? And then we can look at the set and we can identify certain subsets. Okay, but the question will be, how can we recognize and detect when those subsets form subgroups? So a common task will be identifying when a given subset of the group is in fact a subgroup. Okay, because the set will have many, many, many subsets. They won't all form subgroups. To be a group, you have to perform quite well. You have to have the identity, to have all the inverses, closed with the operations, all these restrictions, or at least the conditions you must satisfy. So what we have in the text in this subgroup section here, after the initial examples, are some subgroup theorems. And I have something to say with these subgroup theorems. You can read through the detailed proof here, but really there's one important point to be made, okay? So we've said already that, okay, we've got a subset H of a group G. And this is giving us conditions on H for it to be a subgroup. Now the definition is H has to act like a group by itself under the same operation. So we recognize here the familiar things. The identity element, well, because we've already proved it's unique, there is only one identity element, it has to be in H. The operation has to be a proper binary operation on the set. So in Judson's sense, a binary operation, it has to be closed on the set. The set has to be closed under the binary operation. So if we take any two things in this subset H, we know their product lives in G, because we know G is closed under the operation. But the question is, for H to be a group, the product must still be in the subset H. Because H has to act as a little group itself. So the product of any two elements in it must be within it. It has to contain all the products. So that's part of being a group. It's closed under the operation. We would already know that the product H1, H2 exists, and it is present in G, because little h1 and h2 are present in G. But for H to be a subgroup, it has to be within H. And the similar thing for inverses. If whatever element is in H
for every element little h from H, the inverse of it, which we know to be somewhere in G, but it has to be within the subset H. So these are all restrictions or conditions that the subset must satisfy in order to be called a group. But there's one thing that's missing from there. Which part of the original definition of a group is missing? One of the axioms is missing. Associativity. Why have they left? Why have they forgotten about associativity? So the point here is we don't need to check associativity. It does not have to be said or mentioned again that the operation has to be associative on H. Sorry,
Because they're already in a group.
Yeah. It automatically holds. Because if the operation is associative on G, what that means is for every pair, or for every triple, G, H, and L, G circle, H circle, L is equal to G circle, H circle, L. That's the associative axiom. But if we know that H is a subset of G, do we have to go and prove again and worry that this is true when we replace G, H? No. Okay. Because being associative on G means this equation is true for every triple of elements in G, but H is just a subset of G. So it's easier to be associative on H, and it's automatically true. So if this equation is true of every G, H, and L in G, well, that implies that for every G, H, and L in H, the same equation holds. Okay. Because we're only looking at a subset of the elements. Okay. So if G is a group, the operation is automatically associative on every subset. You okay with that? So that's why it's not listed there in the subgroup theorem. Associativity isn't mentioned again. It doesn't need to be checked again. This proof is just kind of checking all the little details or satisfying all those. Now there's also the second subgroup theorem, which is an alternative subgroup theorem. So basically, to use this theorem means, well, if you want to check that a given subset is a subgroup, you just check all the axioms. Remembering that you don't need to check associativity, but you check the identity, closure, and inverse axioms of H. Proposition 3.31 is like a sneaky little result that just compactifies the work even more. And it kind of incorporates the closure and existence of inverses together in one condition. So to prove that H is a subgroup, you can quicken the work by just checking that every product G with H inverse is in H, where G and H came from H. But there's a sneaky little condition slipped in. You also have to worry about proving that H is non-empty as well. And this is why this isn't really a great advance in the previous one. It's mainly a little bit more, you can lessen the number of lines you use in your arguments, but it really is equivalent to the previous one. Having to check or to separately prove that H is non-empty, really, that's doing the equivalent work of proving that the identity is present. So the work that you might, the identity is present in H. The work or the checking that you do to check that a given subset contains the identity element, that's more or less equivalent to the checking that you might do to verify that a given description of a subset is non-empty. So I think you can more or less dispense with proposition 3.31. This is easier to understand, that to check something's a subgroup, you just check it satisfies more or less the same original definition. Remembering you don't need to check this. Okay, let's get going on the problems. 54 of them, isn't there? Yeah. So the problems fall into two types. Many of them test your handling of the group axioms, confirming or denying that a given operation forms a group on a given set, or that a given subset is a subgroup. Other of the exercises ask you to work out extra consequences of the group axiom. They're like little proofs themselves, or little general results themselves. And generally, the exercises tend to fall into those two camps. So, in the time remaining, was there any particular suggestions of ones you'd like to do, or ones you've been looking at already? Or? Okay, so we'll jump around a little bit. I mean, some of these are specific, you're proving things about matrices and so on. For the submission problems, I've asked you to do, these ones are kind of similar. So I've asked you to do 14. 53 and 54. Okay. 14 is a particular one about forming, and they all relate to things we're going to meet later on. This is an example, your first example of a direct product construction where you take two pre-existing groups, the non-zero real numbers and the integers, and you form a new group by looking at ordered pairs of those things. And 53 and 54 concern special subgroups called the centralizer and this thing which is called conjugation of existing subgroups. So those are examples of things that are going to be important later on. But to do our first problem, let's do 48. And this is similar. So to do 48 will be similar to what we're doing for 53 and 54. So 48, let G be any group. So here's a special subset of G, and it's called the center of G. And it's denoted ZG. The definition of this is the set of everything in G, which has the property that for every element in G, Gx is equal to Xg. So, i.e., Zg is all the elements in G that commute with every element of G. Okay. So elements commute. Pair of elements commute when the product of them, it doesn't make a difference how you order the elements in the product. So the center consists of the quite special elements of G, which have the special property, so those are the x's, that they commute with every other element of G. Why is it notated Z? Zentrum, the German word for center. So it's zentrum. Okay, now a check is a subgroup. Okay, it's certainly a subset of G. So that's what it is. All the elements in G, all the x's in G satisfying a certain condition. So it's certainly a subset. So we've got a subset of G. So we just go and check that it's a subgroup using that first subgroup theorem. Okay. So certainly ZG is a subset of G. That's just how it is, what it's defined as. So we'll use the subgroup theorem to prove that it's a subgroup. We'll use proposition 13 to show it's a subgroup. So the first question we have to think about is the identity in ZG?
Well, you have to test and see if it commutes with every element. So we let G be an element of G. And we worry about E multiplied by G and G multiplied by E.
Are these the same? If they are the same, then E will be in the center. And are these the same? Okay. Which particular element is it? More commonly known as just simply G itself.
Yeah. So the definition of the identity element is that when you multiply it by any other element, it leaves the other element unchanged on either side. So yes, the identity is in the center. That just comes from the definition of identity. Closure is the next condition. So I let x1 and x2 be in the center. I know the center is not empty, so it's not, I'm allowed to talk of elements within the center. So this assumption isn't invalid. Consider x1 and x2. I must prove now that the product x1, x2 is in the center. So I need to prove that x1, x2 is in the center. If I can, then I know the center is closed under the operation. How do you prove something is in the center? You have to prove that it commutes with every other element. So I have to consider a general element, G, from the group, and I have to consider the product x1, x2 times G. Remember, to be in this, for an element x to be in the center, it has to commute with every other element. So here's a general element, G, from the group. There's this product with x1, x2 on the left. I have to show it's equal to G with x1, x2 on the right. How can I justify that? I shouldn't just claim it's equal to. So what I'm trying to do is say that this is equal to G, x1, x2.
Inverses.
Okay.
Equal to G.
So you want to hit this on the left-hand side with x1 inverse or something?
Yeah.
But then you'll have to hit it. Well, see, I don't have anything on the right-hand side yet.
Yeah.
Really, I put there because I know what I want to get, but really I'm just staring at this. So if I multiply it by x1 inverse on the left, but I can't change it, you see, so I have to multiply it by x1 again.
Yeah.
And the x1 x inverse changing, it's just x1 I haven't really changed.
Think about it being associated.
Yeah, something it is the associativity. In particular, we can regard this as x1 multiplied by x2g. So there we're just emphasizing associativity. But what does that cause us to say now?
That x1 and G. No, you know that x2 G is G. X2 from the previous.
Yeah, because x2 is in the center. x2 is a special element from the center. It commutes with every other element. So the x2 can move over.
Remember, we want to get things over the other side of G. Yeah. And play associativity again, bracket it as x1g, x2. And then do the same thing for x1. This is g, x1, x2. So we get what we need. So x1, x2 on the left of G is the same as x1, x2 on the right of G. G wasn't anything, G had no restrictions on G, so it's proved for all G. So x1, x2 is indeed in the center. So it's closed under the operation. Next, we must show that inverses are around. So you let x1 be an element of the group. You need to show that x1 inverse is also present, in the center of G. In the center of G. Well, in order to show that the inverse of x1 is in G, I have to show the inverse of x1 commutes with everything. So I need to consider x1 inverse multiplied by g. And I somehow must build a chain of equations that ends with g x1 inverse on the other side.
Say that x1 to the inverse is the same as you can do re-identifying to do with the identity and x1. No, I think no.
Yeah, no, you definitely, you see, we know something about x1, don't we? We know that it's in the center. At the moment we see x1 inverse, we want to somehow force it to see,
To make x1 appear. You're on the right lines. Remember, we've already seen the theorem that the inverse of the inverse is the same as the element.
the theorem said A was equal to the inverse of A inverse. Here I'm just applying it to this whole element here. So I can introduce two inverses. I haven't changed them. Okay. But now I can bring this inverse in.
So I'll leave the large inverse on the outside. What's the inverse of x1 inverse g?
G
G,
x1.
G inverse
Yeah? Or strictly speaking, x1 inverse inverse, but then the inverse is cancelled. Yeah.
What can I do with that?
Now we've got the x1.
On the right.
Yeah.
What were we looking for again?
Just let Jordan finish this.
I was going to say that the identity, because we're essentially trying to reverse the identity. So it would be G x1 inverse.
Well, that's where,
But it's going to be the other way around then.
well, you want to, I thought you were going to say, you see, we want to move the x1 inverse to the other side of g.
Yeah.
And we've kind of done that here, but it's x1, so we want to keep on playing the game of shifting stuff around. See, now we've got x1, we can use the fact that x1 is in the center. So it commutes with everything. So in particular, it commutes with g inverse.
In particular, it commutes with G inverse. Because x1 is in the center, so you can move it around any.
Right.
Now we've got this inverse to apply, and what happens when you apply that inverse?
x1 inverse G.
G.
G. X1 inverse.
Yeah, remember?
Oh,
My
yeah.
shoes and socks?
Yeah.
It's the product of the inverses, but in the opposite order.
Yeah.
So the inverse of G inverse comes first, so G inverse inverse, in other words, G multiplied by x1 inverse. So there it is, from beginning to end. We've taken any G, and we've popped the x1 inverse over to the other side. So the
x1 inverse is indeed in the center. So ZG is a subgroup. Sorry, rubber on sweat. But that proved the techniques used there are very similar to what you'll need to do for 53 and 54. The centralizer, which is quite related to the center, quite related to the concept, 53 and 54 deals with conjugation. This operation of pre and post multiplying something by an element and its inverse is called conjugation in mathematics. And it's just a name for it. And let's just do that.
It's
Like how you-
far he is.
Okay, over on side. Do people have classes starting at 4? No? Okay.
No, it's fine, we're done.
You do? It's okay. Sorry.
It's all right. Really fun. It's challenge.
Is in this building?
Oh no. That
We
may be why
know
we're still there.
who he is.
Oh.
He or she.
Oh, there's trouble.
You're gonna write the wrong
They are
name.
in trouble.
Name is the wrong name.
It is actually.
That's a sackable offense, isn't
Really?
Very small.
I think with a good enough solvent, you could probably get rid of that.
No.
Maybe melt the ball.